Welcome back to Python for Scientific Computing 1. In today's video, we will see how to implement recursion in Python. Let me start off by giving you a simple analogy of recursion. Imagine you're standing in a line to get a ticket. Your ability to get a ticket doesn't happen till the person in front of you gets his or her ticket. Similarly, that person's ability to get a ticket depends on the person before them, so on and so forth. So until the first person gets the ticket, nobody else will get the ticket. So in a similar way, a recursion is a function that calls itself to perform a calculations. Mathematically, recursion is a functional programming technique where the function calls itself. Note that we can pass functions as arguments to Python, so this allows us to do recursion. Note that we can also call functions within a function, so these two concepts are what helps Python carry out recursion. Every recursive function must have a base case solution. A base case returns a value without the use of recursion. This is like the first person in our analogy getting the ticket. Base case helps avoid recursive functions getting trapped into an infinite loop. But as I said, every recursive function has a potential to get into an infinite loop where the function just keeps calling itself forever. So this is something that we have to avoid. And to do that, we always need to have a base case. Thinking of another way, function calls with higher values depend on the function call with lower values, and this is called hierarchical calculations. Iterative calculations also are similar to hierarchical calculations, but the function calls with higher values may or may not depend on the same function call with lower values. So in some ways, an iterative function can have some elements of recursion, but all recursive functions have to have a function call at a lower value to compute a value at a certain stage, except for the base case. A classic example of recursion is the calculation of factorial. We know that the factorial of 0 is 1, so this is our base case. And then we know that the factorial of any number n is equal to n times the factorial n minus 1. Let's say if n is equal to 2, we know that the factorial of 0 is 1. So then we calculate the factorial of 1, which is 1 times the factorial of 0, which is 1. And then 2 is the factorial of 1, which is 1 times 2. And the value will be 2. So if n is equal to 0, we simply calculate the base case and exit the function. If not, we recursively call the function till n minus 1 goes to 0. So if you look at it, a recursive function, simply we can define factorial n using the def, which defines that it's a function or defines a function. This colon implies that there is a code block. And then my first if statement says n double equal to 0, which means I want the value of n to be equal to 0. When that happens, I'm defining my fact to be equal to 1. Else, I'm going to say fact is equal to n times factorial n minus 1. Remember, this is the same function that I'm calling here, so it will recurse and calculate the value and then eventually return my factorial. To implement it, let's see, factorial of 0 is 1, factorial of 2 is 2, and if I put factorial of 24, I'm going to get a fairly large number. 1 is my base case, and this fact here is the recursion. So the if statement carries the base case, and the else statement carries the recursive function. You can also calculate factorials via iteration, except that the previous value has to be stored when you perform it. So if I do here a function called factiter n, and again I put my base case, I say that if n is equal to 0, and by comparison I have to put double equal to, then I assign a value of 1 to the fact. Else I'm going to say that I'm going to create a range of numbers and loop through where I start with my old number 1 and multiply it with I so that I finish the loop and update my factorial. Okay, so each time I'm multiplying old with the current value of the number, but before I exit the loop, I'm also going to assign that factorial that I just create to the old, and then eventually I'll return the factorial. Again, I get factorial of 0 is 1, which is the base case. If I put 1, I get 1, and if I get 24, I get this number. So you can see that you can do recursion as iteration, although the code tends to be a little longer than simply using the recursive function. Well, recursion we saw leads to a simpler code, whereas iteration typically requires a longer code. It also requires more storage because we are storing additional variables to keep track of those recursive calculations. But inside is recursion faster than iteration. So if I were to do a factorial of 100, and I'm going to use a magic function called percent time it. Magic function is a special type of function that helps us calculate the average time it takes to do this calculation. Remember, your computer is also doing several things in the background. So what it does is it makes several runs, and then it kind of sees when it is, what is the average time, what is the standard deviation associated with it. So if I were to call my factorial function, which is a recursive function, it on average takes about 10.9 seconds plus or minus 51.2 nanoseconds. On the other hand, if I call the factiter, which is an iterative function, remember this is a longer code and it also has additional variables, but it only takes 5.23 microseconds plus or minus 115 nanoseconds. So there is greater variability here, but you generally see that the time is fairly small. So you may not, again, recursion versus iteration, it's a trade-off of physical storage versus using RAM. Another example of recursion is the calculation of the Fibonacci sequence. A Fibonacci sequence essentially is the sequence of the sum of the preceding two numbers of the sequence. So we define Fibonacci of number of 0 is 0, Fibonacci number of 1 is 1. And we start with Fibonacci number 2, which is equal to the sum of these two. So that will be 1 plus 0, which is equal to 1. Fibonacci number 3 is equal to 1 plus 1, which is equal to 2. Fibonacci number 4 is 2 plus 1, which is 3. And Fibonacci number of 5 is 3 plus 2, which is 5, and so on and so forth. So I can generalize and say that my Fibonacci number n is equal to Fibonacci number n minus 1 plus n minus 2. In this case, I have two base cases. The Fibonacci number of 0 is equal to 0, and Fibonacci number of 1 is equal to 1. And for any n greater than 1, I can take the Fibonacci number of n minus 1 plus Fibonacci number of n minus 2, sum them up together, and get the new Fibonacci number. So the recursive solution versus iterative solution, this is my recursive solution. Again, fairly simple code. If basically I use Fibonacci n, and then I say Fibonacci sequence, I'm defining a Fibonacci sequence here. And if I say if n is equal to 0, my Fibonacci number is equal to 0. LF, which is basically saying if n is equal to 1, then my Fibonacci sequence is equal to 1. These two are the base cases. And since I have two base cases, I'm using F, LF, and then L. If it is not 0 or 1, then I'm going to say that my Fibonacci number is equal to Fibonacci n minus 1 plus Fibonacci n minus 2, and then I return the Fibonacci number. Note that although I defined my sequence here, fseq, which is an empty loop, I'm not making use of it, so I could have technically removed that line of code. And again, if I were to put Fibonacci 10, I'm going to get a value of 55, and then I'm going to use the percent time it magic function, and it gives me that it can calculate a Fibonacci number 20 in 2.47 milliseconds on average. If I were to do the iterative solution, you can see that I have to put a sequence which has my base case of 0 and 1. I've already defined my sequence to be 0 and 1. And then I'm going to say that sequence for I in the range of 2 to n plus 1. Remember this, and we are doing n plus 1 because it goes with 2, which is inclusive, all the way to n plus 1, which is exclusive, which means we want n to be calculated. Then I call f sequence I minus 1 plus f sequence I minus 2. Whatever value I get, I append it to my f sequence so that I'm always keeping track of the previous two numbers. And then I return my Fibonacci sequence of n, which gives me all the 10 Fibonacci sequence numbers. Okay, so again, if I do f iter, you can see that if I get f iter of 10, it's going to give me 55, which is the same answer I get here. And if I do time, it is 1.16 microseconds, way faster than 2.47 milliseconds that we are seeing here. So sometimes iterative solutions are faster, but recursive solutions lead to simpler code. So many times you can do what is recursion using iteration, albeit it'll be a slightly bigger code. Okay, and when possible, iteration is definitely better than recursion in Python. The quicksort is a sorting technique. The approach essentially starts with partitioning the list. We start with a pivot element, and then we compare the pivot elements to the other elements of the list. And based on the pivot, we divide in the list into three sublists. The smaller list, where the numbers are smaller than the pivot, the greater list, where the numbers are greater than the pivot, and equal list is where the numbers are same as the pivot. Then we apply the partitioning algorithm to recursively from the smaller and the greater list. And we say that the sorted list is smaller list plus same plus greater list. This recursion will proceed till all elements are sorted. Again, to show you the code, we basically say that we have define a function qsort, and we say that if the length of the list is less than or equal to 1, it means if I just send you a null list or with a single element, then the sort list is equal to the list. This is basically my pivot. And then what I do is else I'm going to have to pivot and say my list that I'm sending here, I'm going to pick the first element as a pivot. I could have picked any element, but it's just easy to pick the first element. Then I define two other lists. One is a bigger list, one is a smaller list. And then I also define an equal list, all as empty lists to initialize. And then I say for item in list, if item is greater than pivot, bigger dot append the item. Else, if the item is less than the pivot, I'm using elif because I have three conditions. I say smaller dot append is equal to item. If these two conditions are not met, then the item is the same. The item that I'm comparing is the same as my pivot, in which case equal dot append is the item. And eventually I say my sort list is qsort, which is the function that I am applying to the smaller plus equal plus qsort bigger, and when I do this, it will return me a sorted list. So if I were to give a list of 1, 3, 6, 4, 12 to 18, 16, 19, apply qsort, you can see that the numbers have been sorted. Python allows for functional recursion. Recursion, again, is when a function calls itself as part of the calculation. Recursion is useful for hierarchical calculations, where the future calculations depend on previous calculations. This may or may not be the case with iteration. So all recursive functions are iterative, but not all iterative functions are recursive. Recursion requires a base case where the function value is known. Otherwise, if you don't have this base case, the function will just keep calling itself, not knowing what to do, and you get into an infinite loop. So we must have a base case. Of course, we saw that like with the Fibonacci sequence, we could have more than one base case, in which case you use the if, elif, else syntax. Recursion is useful when we divide a problem into parts to solve it. The qsort example that I showed you showed how we divided and conquered the problem by taking a number, pivoting, and then taking the lower and the upper, and then performing recursion on that. Recursion, as I said, is closely related to iteration. Iteration sometimes may be faster, but recursion often leads to a simpler code once you understand what's going on. Recursion suffers from what we call the curse of dimensionality, which means that the computations will become slower and slower as the number of recursive calculations increase. This is because even though recursion is just showing you one number to you, in reality it is storing all these intermediate calculations internally and trying to make use of it. So that does take up some memory, and that does take up the speed with which the calculations can be made. So I hope you have an understanding of recursion from this video. I'll see you in the next one. Till then, take care and goodbye.